The content in this presentation is covered on pages 191 through 194 of your textbook, and it's meant to help you achieve Learning Objective 41, which is to describe or sketch the three-cell model of global circulation. Be sure to skim those pages before watching the video and read the chapter carefully before attempting the online quizzes. Our knowledge of global winds comes from two sources: the patterns of pressure and winds observed worldwide, and from theoretical studies of fluid motion. We'll first consider the classical model of global circulation developed largely from the average worldwide pressure distribution. And then we'll modify that model by adding more recently discovered aspects of the atmosphere's more complex motions. One of the first contributions to the classical model of global circulation came from George Hadley in 1735. Well aware that solar energy drives the winds, Hadley proposed that the large temperature contrast between the poles and the equator creates a large convection cell in both the northern and southern hemispheres. In Hadley's model, warm equatorial air rises until it reaches the tropopause, where it spreads towards the poles. Eventually, this upper level flow reaches the poles, where cooling causes it to sink and spread at the surface as equatorward moving winds. As the cold polar air approaches the equator, it's reheated and rises again. Thus, the circulation proposed by Hadley has upper-level air flowing poleward and surface air moving equatorward. Although correct in principle, Hadley's model doesn't take into account Earth's rotation. In the 1920s, a three-cell circulation model, which considers Earth rotation, was proposed. Although this model has been modified to fit upper air observations, it remains a useful tool for examining global circulation. This figure illustrates the idealized three-celled model and the surface winds that result. In the zones between the equator and roughly 30 degrees latitude, north and south, the circulation closely resembles that Hadley convection cell. So we call it the Hadley cell. Near the equator, warm air rises and releases latent heat during the formation of big cumulus cloud towers. And it's believed that provides the energy that drives the Hadley cells. So as the flow aloft moves poleward, the air begins to subside in a zone between 20 and 35 degrees latitude. Two factors contribute to that general subsidence. As upper-level flow moves away from the stormy equatorial region, radiational cooling becomes the dominant process. As a result, the air cools, becomes more dense, and begins to sink. The other factor is that the Coriolis force becomes stronger with increasing distance away from the equator, and that causes the poleward moving upper air to be deflected into a near west to east flow by the time it reaches 30 degrees latitude. And this restricts the poleward flow of air. So, in other words, the Coriolis force causes a general pileup of air, a convergence aloft. As a result, general subsidence occurs in the zones between 20 and 35 degrees of latitude, and that subsiding air is relatively dry because it's released all its moisture near the equator. In addition, any adiabatic heating that occurs during the descent further reduces the air's relative humidity. And as a result, this subtropical zone caused by subsidence is the site of many of the world's greatest deserts, such as the Sahara, the Great Australian Desert, the Atacama Desert. Because surface winds are sometimes weak between 20 and 35 degrees latitude, this belt was named the horse latitudes, because early Spanish sailing ships crossing the Atlantic were sometimes becalmed and stalled for long periods of time in those waters. If food and water supplies for the horses on board became depleted, the Spanish sailors were forced to throw the horses overboard. From the center of the horse latitudes, the surface flow splits into two branches, one flowing poleward and one flowing towards the equator. The equatorward flow is deflected by the Coriolis force to form the reliable trade winds, so called because they enabled early sailing ships to move goods between Europe and North America. In the northern hemisphere, the trades blow from the northeast, while in the southern hemisphere, the trades are from the southeast. The trade winds from both hemispheres meet near the equator in a region that has a weak pressure gradient. That zone is called the doldrums. Here, light winds and humid conditions provide the monotonous weather that's the basis for the expression, the doldrums. And in the three-celled model, the circulation between 30 and 60 degrees latitude, north and south, is called the ferrule cell. That was proposed by William Ferrel to account for the westerly surface winds in the middle latitude. So those prevailing westerlies were known to Benjamin Franklin, perhaps the first American weather forecaster, who noted that storms migrated from west to east across the colonies. Franklin also observed that the westerlies were much more sporadic and therefore less reliable than the trade winds for sail power. We now know that it's the migration of cyclones and anticyclones across the mid-latitudes that disrupts the general westerly flow at the surface. Because of the significance of the mid-latitude circulation in producing our daily weather, we consider the westerlies in much detail in courses like this. The circulation in a polar cell, way up at the top of the globe, is driven by subsidence near the poles that produces a surface flow that moves equatorward. This is called the polar easterlies in both hemispheres. And as these cold polar winds move equatorward, they eventually encounter the warmer westerly flow of the mid-latitudes. The region where the flow of cold air clashes with warm air has been named the polar front. The significance of this region is important in the development of the mid-latitude cyclone and in the storm cycles and seasons of the mid-latitudes. Due to Earth's rotation, rather than being a single convection cell that transfers energy between the equator and the poles, the global winds crudely resemble a three-cell system. The convection cell from the equator to roughly 30 degrees latitude is the Hadley cell, from 30 to 60 is the Ferrel cell, and from 60 to the poles is the polar cell. Use the content provided on the Canvas site, as well as any outside internet sources that you find to verify you can formulate answers to these 5 questions. If you can comfortably answer them, you're in great shape for the next test. If you are stumped by them, start a discussion on the Canvas site or ask me for help.